Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from limits involving the inverse trigonometric function along with the fractional part function, right? So here we have to discuss this limit, that is limit x tends to 0 sine inverse, and here we have the fractional part of x, right? So here what we will do, we'll find out the right hand limit and the left hand limit of this function, that is sine inverse of fractional part of x, right? And when x approaches to 0, right? Okay, so here let us first see the fractional part of x, right? So the fractional part of x is defined as x minus the greatest integer of x, right? And we know that the domain of the fractional part of x is the set of all real numbers, but the range is from 0 to 1, right? Okay, so now let us first calculate the right hand limit, right? So we can now write right hand limit as limit x tends to 0, and here we have the positive sign to indicate that we are approaching towards 0 from the right of 0, right? So here we have 0 and we are approaching from the right? So this is x is equal to 0, right? And here we have sine inverse of a fractional part of x, right? So we can now write limit x tends to 0 positive, and here we have sine inverse of a fractional part of x can be written as x minus greatest integer of x, right? Okay, so now here we'll put x is equal to 0 plus h, right? So here h is a positive quantity, and h, it lies between 0 and 1, but h is very small, right? So h is infinitesimally very small, and here x is 0 plus h, right, which can be written as simply h, right? So when x tends to 0, then obviously h tends to 0, right? So now the right hand limit can be written as limit, and we have h tends to 0. Now we are writing this right hand limit in terms of h, right? And here we have sine inverse, and for x we can write h, and for here x we can write h, right? Okay, so now we have this expression, right? So here we cannot directly substitute h is equal to 0. Why? Because see, here we have the greatest integer of h. Now see, h lies between 0 and 1. So when h lies between 0 and 1, then the greatest integer of h is 0, because of the definition of greatest integer function, right? Okay, so now here we have 0, right? So now we can write limit h tends to 0, and we have sine inverse of h minus 0, right? So this is the limit h tends to 0, and we have sine inverse of h, and now we can take h is equal to 0 here. So we have sine inverse of 0, which is equal to 0, right? Okay, so now the right hand limit is equal to 0. Now let us find out the left hand limit. So now the left hand limit, it can be written as a limit and x tends to 0 minus, right? So this negative sign shows that now we are approaching towards x is equal to 0 from the left of x is equal to 0, right? And here we have sine inverse of a fractional part of x. So this can be written as limit x tends to 0 minus, and we have sine inverse of x minus greatest integer of x, right? Okay, so now here we'll take x is equal to 0 minus h, right? So here x is equal to 0 minus h, because here we are very close to x is equal to 0, but towards the left of x is equal to 0, right? And in the case of right hand limit, we were at this point, which is very close to x is equal to 0, but it lies towards the right of x is equal to 0, right? So this point is 0 minus h, and this point was 0 plus h, right? Okay, so now x is equal to 0 minus h, which is simply minus h, and when x tends to 0, h tends to 0, right? And obviously h is a positive quantity, and h lies between 0 and 1, right? So now the left hand limit takes the form limit h tends to 0, and we have sine inverse of 0 minus h. Here we'll take 0 minus h, or simply minus h. We can take it as simply minus h, and here we have greatest integer of minus h, right? Okay, so now here we cannot directly substitute h is equal to 0 here, right? Because see, here we have greatest integer of minus h. Now see, to get the value of greatest integer of minus h, we have h lying between 0 and 1, right? So if we multiply throughout this inequality by minus 1, we have 0, and here we have minus h, and here we have minus 1, right? So when we multiply throughout by minus 1, the direction of the inequality get reversed. So this inequality can also be written as minus 1. Here we have minus h, and here we have 0, right? So this inequality indicates that minus h, it lies between minus 1 and 0, and when minus h lies between minus 1 and 0, then the greatest integer of minus h must be equal to minus 1, right? So here we'll take minus 1. So now the left hand limit is equal to limit h tends to 0, and here we have sine inverse of minus h minus and minus 1, right? So this is limit h tends to 0 sine inverse, and here we have minus h plus 1, right? Now we can take h is equal to 0 here. So we have sine inverse of minus 0 plus 1, that is sine inverse of 1, right? And we know that sine inverse 1 is pi by 2, right? So this is 90 degrees. So because sine pi by 2 is equal to 1, so sine inverse 1 is equal to pi by 2, right? So here we see that the left hand limit is equal to pi by 2, right? So right hand limit and the left hand limit of this function when x approaches to 0, both are finite and both the limits exist, but the right hand limit is not equal to the left hand limit, right? So for the existence of limit, the right hand limit should be equal to left hand limit, right? But in this case, the right hand limit is not equal to left hand limit, because 0 is not equal to pi by 2, right? So we can claim that the limit of sine inverse of fractional part of x when x approaches to 0, this limit does not exist, right? So viewers, this is how we can solve these type of problems.